So my name is Kevin Urrutia. I'm currently an undergraduate electrical engineer pursuing his interests in robotics as well as the environment and trying to mesh these two together. Currently, I'm working under Dr. Cardis, and today I'll be talking about the autonomous soil moisture logging system that I have created over the past 10 weeks. But first, I want to talk about the importance of soil moisture. So if you think about it, agriculture is a business. Agriculture growers need to have a certain threshold for the amount of crops that they need to grow per season in order to make a profit. So there's certain things that they need to monitor. One of these things is soil moisture, and soil moisture can help growers increase their amount of crops per season through the following things: increase percent yield of the crops, fends off disease and pests, preserve soil health and nutrients, and controls heat exchange. So these are all things that growers need in order to have a growth in revenue per season. And one way that they can control these factors is to monitor the soil moisture. So that leads us to our soil moisture mapping system. This system is a way to map the amount of soil moisture that you have per percent volume per acreage on your land. So the way that this works is that you take the original mapping of your land. So let's say it's 25 acres. The example that we have here, let's say it's 25 acres. And we overlay on top of this the soil moisture hues that we can have on different parts of our land. So there's a reddish undertone, which means that there's less percent by water volume in the soil, and a bluish undertone, which means that there's a higher percent by volume in the soil. So we can take this map and let's say that the grower has a specific plant. Let's say it's grapes, for example, and grapes can have a specific soil moisture that they require to have optimal levels of growth. So then we take this map and then we see, say, on all of our 25 acres, grapes are growing in these locations. We need to water more by percent volume for grapes to grow optimally, or less than percent volume for grapes to grow. And we can use this map to therefore schedule watering system and increase our irrigation efforts to reduce the amount of water we're using, use the water more efficiently, and use our overall resources more efficiently, therefore reducing the cost for growers and then increasing the revenue for growers. The current solution is to actually have professionals come out and do this soil moisture mapping. It's very prevalent in California. California, as we all know, is very prone to drought, prone to inclement weather, so that decreases the soil moisture. This map provides insight into areas where soil moisture is needed, and the way that soil moisture works is that it's affected by both the type of soil as well as the elevation of the soil. So type being, let's say, soil, the clay is the one that retains most soil moisture, and sand being the least. So going back to our sand, or 25 acres of land, different areas can have different amount of soil types and therefore vary in their soil moisture levels. So this is something that we need to monitor. We also need to monitor the elevation. Elevation means that there's more, as we get higher in elevation, there's less soil moisture on the top of the land because that it all leaches down. So we need to monitor these locations to have optimal levels of soil moisture. It also allows us to create a custom monitoring schedule that I mentioned previously. If this is a big caveat, if we do this process enough and it's very precise, and then it leads to our benefits that we mentioned previously for the growers, like percent yield growth. Consequent problems being is that it's a high monetary cost because it needs to be done by a professional, like I mentioned previously. It requires large labor costs and it's very imprecise. So meaning that how does the professional know when exactly or where exactly on your 25 acres of land to measure? It's not feasible to measure all 25 acres, correct? So the professional needs to either do it randomly or by discretion of the grower. The grower can say, hey, professional, I'm having issues in this location. Can you go check it out, test the soil moisture, and tell me what's wrong? And then we can get like a soil moisture map based on this. But the problem is that it can't be conducted often enough. So then we have this issue of optimization. We can't have our optimized watering system if we have an outdated soil moisture map. So these are our proposed solution. We actually have in our lab the soil moisture sensors that are used by professionals, and we're actually going to retrofit that soil moisture sensor to this Bluetooth module that you see on the top. And then we're going to retrofit it to be able to log the information and then be able to transmit it through Bluetooth to this autonomous robot you see at the bottom. And we modify the software stack of this robot so that it knows the GPS location of this soil sensor station. It goes to this location, gets the information, and then goes on its merry way. The benefits of this proposed solution is that it reduces the monetary cost. So it provides a single purchase. You buy the robot once, you buy the soil moisture logging system once, and depending on how many you buy, you can have it all over your land. So it's a single monetary cost. It reduces the labor process because the robot already knows where to go. It already knows the GPS location of each soil moisture sensor. And so it does not require user input. It's more precise because depending on how many logging points you can have them all over your land, 25 acres. We can get to these 25 acres much more easily than a professional can. The robot can conduct other processes at any time. So the only process that it needs to conduct for our purposes is to actually just go to these sensors, get the information, and then be on its merry way. But in the way that it's going, on the way to go to that location, it can actually snapshot pictures, let's say, of the area and do image processing. It's completely free to do these other things, making it a more optimized system. Here we're going to get into our system diagram for the actual soil monitoring system. We have a go-between microcontroller between the feather, the microcontroller I showed previously, and the SDI12 bus, which is the sensor. It has a UART connection between all of these. So the UART connection is a byte transfer of data information between a wire. So the nano gets the information from the SDI12 bus. This includes the soil moisture information, all these good and wonderful things. This nano then transmits it directly to the feather, and then this feather transmits it to the raw spot through Bluetooth connection. This is all powered through a solar panel. We originally do 12 volts for the SDI12 bus, which is required by the sensor. Then we do 5 volts and 3.3 for the two microcontrollers. We have our state machine here. This is exactly how the state machine is going to run, or the processes of the microcontroller is going to happen. So we're going to start off on our initialization stage. And we want to check first if the actual robot is connected or not. Because if it is connected, we don't want the robot to wait, because that means it's a non-optimal system. We want to immediately start transmitting information. But let's say it's not connected for now. We go to collect for about 10 minutes. We collect the information, we collect all this good stuff, right? And then as soon as it's 10 minutes, we stop collecting and we start saving. Problem is that we don't want to collect for too long, because the soil moisture doesn't change all that much unless there's an irrigation event or a larger event like that. And then as we save, and then we finish saving, we go to wait stage, we wait for about 30 minutes, and if it's not been connected, we go back to collect. But if we have been connected to the robot at any point of this, we directly go to transmit. We do transmission, and we do this transmission based on a queue. A queue is a line. So let's say you enter the line first, you get helped out first. So then you exit first, correct? So then we transmit the information. These files are made first. We transmit that file first. We delete that file from the SD card. Then we transmit it. And then we do this transmission until the actual line is finished and we no longer have files to send. Then we go to our software stack. The software stack includes an SDI12 bus through the UART connection. This goes to a real-time clock and SD card. The SD card saves the information from the SDI12 bus, the real-time clock, saves the current date and time so that we know exactly which file is being saved and pushed. The Bluetooth, it gets the pointer for the queue, pops off the queue, so it transmits that file and sends that data, the SD card data, sends it over Bluetooth, and that's the software stack. We actually did some experiments using the raw spot and the feather. As you can see, I sent over some dummy data. I sent over some dummy data from the feather on the blue screen, as you can see there, and then I received it on the black screen, which is the raw spot. So they're not connected other than the Bluetooth. I also did some SDI12 experiments, so the sensor experiments. Originally, I used the breadboard, but we changed that at the very end to use the nano. And then the nano connects to the SDI12 bus. We do a logic convert between 5 volts to 3 volts, which is necessary to communicate between the microcontrollers. We send that over, and then we have that information ready to go. Some challenges that we actually faced was we originally only had one feather, which is the original microcontroller that sends Bluetooth information. Problem being is that the Bluetooth used all the timers, and the SDI12 bus required one timer, so there was a conflict. So one way to get around this was to use the Nano as a go-between. This is not a very good optimized system, so we need to fix this. One way to fix this is to use Raspberry Pi Zero, which you can see here. Problem being with this Raspberry Pi Zero is that it's too complex. It's an actual computer, so it might be too overkill for this project. So we need to do more research and looking up onto see what's actually going on, which one's the best board. Then we're going to go introduce our solar panel, continue field testing. I want to thank Rise for giving me the opportunity to be able to speak to you guys today, for giving me all these insights into research. I want to thank the lab, the ARCS lab, to giving me the experience to be able to talk to you guys today and to know exactly what I want to do. I want to do robotics, and this is the perfect opportunity to get introduced. I want to thank the Digital Agricultural Fellowship for funding me today. Here are the references for the photos I've been using, and that's it. Thank you.